Welcome to a pragmatic introduction to cryptography. It's pragmatic because we're going to talk about using cryptography in practice. So composable tools, how they're used in everyday systems, not the formalisms, we'll use some formalisms to the extent that they're useful to understanding what the tool does and what we can rely on it to do, but not the number theory, for example, underpinning the lattice schemes or things like that. Introduction, because we're going to start from an assumption of not knowing anything about cryptography, just vaguely knowing what it is. There's a QR code that drops you into this same Google Doc that I'm using. You're welcome to drop comments if we talk about something and I go off script and you want to take a bit of notes that's what we talked about. That's actually helpful. Feel free. I'm trusting people not to be silly with the QR. I'm sure that as soon as we put it online, I will regret this instant. Okay. Start with a bit of introduction. I'm Filippo. I use he, him in English. I use the male pronouns in Italian. And I am an open source maintainer as the main title. And I'm a cryptography engineer. So my path has been a little weird, in part because cryptography engineering is a field now. Was not a field. 10 years, I'm kind of amazed that there are actual entire courses in cryptography engineering, not a thing 10 years ago. 10 years ago, you could do cryptography, math, and you would barely see any code. Like the code was for, sure, after all of the problems are solved, somebody will implement it. That's easy, right? And if you were implementing cryptography, you were like somebody that had enough self-esteem, potentially too much, to think, yeah, of course I can do that. It was a fun time. It had consequences. Anyway, cryptography engineering is a thing now, but I don't have a formal background, partially because there was no way to acquire a formal background in cryptography engineering back then. I started by working at Cloudflare. In 2014, I got there because of the Heartbleed vulnerability. Does anybody know what Heartbleed was? You're too young for that. Oh, right. Heartbleed is a software vulnerability that happened. You don't count. It's a software vulnerability that happened 10 years ago. And it was a vulnerability in the OpenSSL library. And it had almost nothing to do with cryptography, the theory, but everything to do with cryptography engineering and the practice of implementing cryptography software. OpenSSL had this implemented the kitchen sink. It was the library that everybody used to implement TLS, much more than that is true today. And TLS is the protocol of HTTPS, the S in HTTPS. And they had implemented absolutely the kitchen sink. And the kitchen sink included a protocol level extension to ask the server if it was still there. And to ask the server if it was still there, the client would send some bytes, a variable number of bytes, and the server would echo them back. Heartbleed, the vulnerability, was a vulnerability where you could send 1 byte and say, oh yeah, I sent you 10 kilobytes. I totally did. Why did it support that many bytes for something that's just a ping? Moving on. Yeah, I totally sent you 10 kilobytes. And the server would respond with 10 kilobytes. Can you guess where the remaining 9 kilobytes and 999 bytes came from? Random memory. Just stuff that was there. And of course, keys were in there. It was fun. You could ping a server and get back the certificate's private key. It was a good time to do cryptography. Anyway, I built a silly website to scan other websites for Heartbleed vulnerability because a person that I respect, Adam Langley, had made one for the previous catastrophic bug, which was go to fail, which I later learned was reported because a friend heard 2 people talk about it at a bar and talking about how they were going to sell it. And so he reported it anonymously, and that's how we got go to fail. But that's another story entirely. Another software bug that has nothing to do with the theory of cryptography, but everything to do with the implementation of cryptography. If you see a pattern, yes, yes, cryptography is sort of um, the software engineering for perfectionists. It's software engineering where you can absolutely spend 3 months to write 500 lines of code and you not get fired for it, which is why I'm in this line of work. And we'll talk about testing and we'll talk about all of those considerations a little bit today and again in one of the last lessons, wrapping up after we go through the actual tools of cryptography. Anyway, Hartley made a test website that got famous, that got me into Cloudflare. Cloudflare was a bit of a pirate ship, 50 people, 10% of the internet. Fun times. I joined thinking I was going to do cryptography, end up doing DNS. I implement DNSSEC, which I think makes me qualified to say that DNSSEC is a terrible idea. Which a lot of cryptographers do say that, but then they get told by the network and DNS people that they don't know networks and DNS. And guess what? I implemented it, possibly the largest scale that was ever implemented, and it's still a bad idea. Anyway, moving on. Cloudflare, we use Go, Go programming language. Are you familiar with Go? No, yes. So Go is a programming language developed at Google now 12, 13 years ago. And it's a compiled, statically typed language that looks C-like, but it feels the same space as Java, really. That's the quickest way to put it. And these days, most of the things that you think of as the cloud, Kubernetes, Docker, lots of APIs, microservices and stuff, those are usually implemented in Go. Go is designed to be pretty simple, to make it easy to collaborate and work on a shared code base. It gets pretty out of the way. It gives no satisfaction to people that want to feel very smart. So there are people who don't like it, which fair enough. And to be fair, there would be a few things that to do cryptography would be nice to have, but the language doesn't have because it tries to keep the complexity of the language to a minimum so that you can think about the thing you're actually doing. It does make my job interesting. Anyway, Go programming language was at the beginning. Back then, Cloudflare does a lot of Go, so I get into Go. I end up joining Google to work on Go, and I end up maintaining the cryptography packages in the Go standard library. Fast forward a few years, I end up team leading the Go security team. I am not a particularly good manager, as I learned. No thy limits. And anyway, I left around 2022 to become an independent open source maintainer, which is a whole other thing. You can look up Geomis here. If you're interested in that part, I have opinions about open source. They're not the point of this course. So yeah, that's the perspective I have. I am in charge of implementing cryptography for probably between 2 and 5 million developers, and they then use it to bring services to billions of users because it's used. Yes. And including things like the Estonian identity and election system, which I try not to think too hard about. Can you think what the threat model of the Estonian elections is? Can you think who the primary threat actor is? Think geographically where Estonia is and who has an interest in influencing its elections. Yeah, I sleep well at night. It's great. No, I actually enjoy this. But that's my perspective. I work on implementation and I weigh up the stack when it's necessary for improving implementation outcomes. So I ended up co-developing specifications. I do a lot of research around testing and how to improve testing of software, how to make specifications more testable, how to make them easier to implement. I have a lot of opinions on what we can push up the stack, because by the time you have to implement it, sometimes it's not designed in such a way that you can do it particularly safely. Okay, so I think that's my background, how I got starting cryptography, indeed, there was not much formal background. There's a Coursera course, which may be still free. I think the videos are definitely somewhere because I think Dan did not want them to be behind a paywall, by Dan Bonnet. It's pretty old, but it has it's a good complement for this course in that this course we're going to talk about the very concrete and practical things, while that goes into the theory a bit more sharply. And then on the other side of the spectrum, there is CryptoPals, which, if you do enjoy programming, is extremely fun. And you can totally come here with like a CryptoPals problem that you're not getting or that you want some help with. And I would love to chat about CryptoPals. CryptoPals is a set of challenges where each of them gets you to implement a little crypto system. And then tells you, good, if you implement it like that, it's broken. Now break it by doing this and this and extract the key and like it over and over. And you start at tiny little things, which do happen in practice when developers implement their own crypto. And then you move all the way into, okay, so here's a paper that broke TLS a few years ago. Go. And yeah, it has a nice curve. I really enjoyed it. All right, so the course, a few logistical things. Textbook. Serious Cryptography, second edition by J.P. Omason. I am very glad this exists. What's that? Can we close the door? Thank you. I'm extremely glad that this book exists because before it was kind of hard to find a reference for actual book to do cryptography engineering, and people would go and pull up cryptography engineering, the book by that title. Okay, and cryptography engineering, the book by Bruce Schneier, I think, is old. Extremely old, as in some of the algorithms that you need are not in there. Some of the things that it says we've over time learned not to do, which fair enough, because long time has passed. We're going to talk a bit about phases in cryptography engineering. Yeah, the ISBN is in there. JP is great. So you know, if you want to buy it, it's a good book. If you don't want to buy it, ping me. Cool. Recordings, we'll record them all, upload them a couple days later, something along those lines, so that they're available before the next one. I would like to structure this such that you read the chapters in the book, not study them like an exam, but like read to get an idea of the things before the lessons, because otherwise I'm here being like, so counter mode and what's the point, right? You can just get that from the book. So I will tell you which chapters are cover the topics of the next two lessons for next week. Read up on those. Come with questions. Come with things you didn't get. Come with things you want to know. If you just let me talk uninterruptedly, I will try to stay on implementation, introduction, and the things that now I'll mention from the program. But I am very happy if you take me on side paths, you ask me about implementation trade-offs, all of these things. I don't want to get too deep because it's a fractal, so I haven't put them in there because I could probably speak for 20 hours about implementing a single one of these algorithms, and I think a total of 3 people in the world would enjoy that. But if at any point you do want to push me on a little side topic, do it. Like, to interrupt me, please. Let's not make this uninterrupted 20 hours of me talking. Let's not. Okay. Questions so far? No, I just told you to. You're not following. Nothing, not about the course, nothing about path background. Okay. Then program. Today, introduction, what cryptography does, security levels, randomness, fundamentals that we'll probably use and want to be able to refer to without explaining. Like when I say something has 128 bits of security but has problems with multi-target attacks, that's just a tool that's useful to have later to talk about things. So that's today. And today is probably the least, the one with less diagrams and with less concrete things to build and break, because it's fundamentals. It's how to think about cryptography, how to structure this. And truly, it does help me if you help me and help others watching the recording. If you tell me like what things don't make sense I've been doing this for 15 years. Some things make sense to me and I might skip over them and like, oh yeah, of course the attacker can do that and that and not that and that, because of course the attacker has these powers and not those. If something doesn't make sense, do poke me, because I think this is useful framing for then the rest of the course. Rest of the course. Symmetric encryption, the thing that most people think about as encryption. So you have a key, you have a secret message, you want the message to stay secret and not get tampered with. So that's stream and block ciphers, nonces, authenticated encryption. It's an interesting field. Funnily enough, there are some cryptographers that never touch it and find it too hard. And I always found the symmetric stuff too mathy, and the symmetric stuff just like, yeah, these are like funny little giochi matematici. Like these are puzzles, and you just compose them, and there's nothing magic about it. Like while asymmetric cryptography, there might be somebody that comes along and goes like, yeah, you just do a LLL attack with lattices, and you bring that into a matrix, and then close the key. Sure, I no idea how I was supposed to know that, but yeah, you do you. Symmetric cryptography doesn't have that. It was all there, and if you had like too small a space somewhere, you could have seen it. And I find that reassuring. Hashes. Hashes are usually actually what I like to start from when I have less time, because they're just the most versatile tool of cryptography. You can build everything symmetric from a hash, and vice versa. You can take a symmetric block cipher and build a hash. And we'll also see a bit how we ended up where we are is a bit path dependent. If we were to reinvent the entire field today, we would probably end up with different, like, instead of having A's built on B's, we might have B's built on A, and vice versa. We'll see that in those lessons. PRFs, ciphers, maths, ciphers not again. Maths, which are authentication codes, key derivation functions, and how to turn each into each other, which is the interesting exchange thing. And that's next week. Week after, asymmetric cryptography. So yes, all of this gets you have a key and somebody else also has a key, or you in the future also have a key. Asymmetric encryption lets you do things that are not that. So I have a private key, you have a public key, you can encrypt to me, or you have a private key, I have your public key, I can check your digital signature, which are the two main large things. And then there's a long tail of other fancy things, which are not in a different lesson. That used to be RSA and ECDSA. It's not, because I had to change most of the program, and we'll chat about that in a minute. Anyway, key exchange used to be about Diffie-Hellman and prime order groups, and I have so many opinions about prime order groups that are now completely useless. Anyway, but it's now instead about chems. So key exchange is when you open a connection, you establish a communication channel, and you want to make sure that whoever is intercepting that channel cannot decrypt the contents unless they're one of the two parties of the communication. We'll see that this is not sufficient alone, because if you don't also know who you're talking to, then you can open a secure connection to the attacker. The attacker opens a secure connection to the destination. You think you're talking to a destination, instead the attacker is in the middle and is relaying. But the key exchange mechanism is the thing that just does the first establishment. And you can intuitively see how that requires asymmetric cryptography, because if you only have tools that require shared knowledge of a key, how do you open a connection to a stranger and establish a secure channel if you don't already share some key material? Hence, asymmetric cryptography, key exchange. Then, week after, signatures, which are the other main part of asymmetric cryptography, and are the ones where you with a private key sign something, I with a public key can verify the signature, and nobody can make a signature for a message that you did not sign. We'll see how that works, how we use it. Used to be about ECDSA, EDDSA, Schnorr, Fiat-Shamir, and well, Fiat-Shamir, we still use it. And I have so many opinions about those, and those are useless now. Anyway, protocols. So all of this is considered, is what most people think about cryptography, about as cryptography. It's a surprisingly small part of my job. A lot of the work is the stuff you build on top. And protocols are the specifications for how you compose these tools. There's a lot of composition in cryptography engineering. You have a key exchange, you have a signature, great. You think, well, I can open a connection, use a signature to make sure that the other party is who I think it is. I have a way to communicate securely. Draw the rest of the fucking owl, the meaning with two circles. And protocols are the rest of the owl. So all of the things that define how you connect, how you authenticate, what parts do you sign, what parts you don't sign. So many of the interesting attacks are in protocol land. So that's one lesson, which might end up to, we have one of Slack. So cool. And I like to say that everything is a protocol. Sometimes people think they're doing cryptography and they just compose a bunch of stuff and they're like, oh, but it's fine. I'm not making a whole protocol. I'm just using a couple things. No, you just made a protocol. And probably it's bad because you weren't thinking about it like a protocol. And so you just put together some components and use them in a certain way. That is the definition of a protocol. But if you just hand roll one, you will probably forget all of the stuff that we learned in blood over the last 20 years of protocol design. So yeah, everything is a protocol. We'll see protocols. Fancy crypto. This is a term that my colleague, extended colleague, Sophie Schmink likes to call the other part. Like there's symmetric encryption, there's signatures, there's key exchange, and then there's fancy crypto, which is all of the other things. Zero knowledge proofs, those are very fun, and we might still have them after quantum computers, which is nice. Threshold signatures, meaning signatures where instead of one person signing something with one private key, you need n of n keys to collectively decide to sign something and coordinate somehow a protocol to produce the signature. Multi-party computation, which is the generalization of that concept where multiple parties contribute to the same computation in such a way that you can bound the limits of what each party can do. Like, for example, we all collaborate, and by collaborating, we calculate the result of an election, but nobody in the group can neither see the votes nor alter them unless they collude with more than a majority or things like that. Fully homomorphic encryption, so encryption that allows you to still search a database after it was encrypted. And here we're getting further into stuff I know less about. I'll be honest. The FHE is not my field, is an entire field, the size of cryptography engineering, MPC pretty much. And on the other end of the spectrum, instead, there's Merkle trees, which are just hashes, are one of my favorite tools, and they let you do so many cool protocol things. We'll talk about those. And then one lesson is for realities. So all of this stuff is still kind of theoretical blocks. In practice, how does that look like? There's a lot of human to it. There's the human part of doing the job. So how we write specifications, how we collaborate on deciding how specifications are done, what things do we prioritize in specifications? Because sure, the math works, but if you don't make it easy to use, for example, easy to implement, it will get implemented wrong, and it might as well be broken the math. What's the point? How we evolve those specifications is a whole thing. Then there's the keys. Great, you build a thing that is secure if the keys are secure. Does it require people to hold on to their keys? Are you assuming that the average human will manage to secure and keep a key for a long period of time? Great, your system is useless. Congratulations. Fantastic job on all of the protocol design and the implementation and the specification. Was your assumption that the same human today can have the same key in 5 years, not have lost it, and not have compromised it? Completely useless. And all of the stuff we built around instead tolerating for key rotations and identity management and so on. Libraries, we are not constantly re-implementing this stuff. We have people implemented in certain languages in central libraries, and we make them reusable. Testing, I can give probably 20 hours of opinions and techniques on testing software alone, because cryptography engineering is software engineering, and then you test it until you're sure there's truly no bugs. I think I'm at 3 layers deep of testing tests at this point, because you write tests, then you realize that you want to know if your tests are complete, so you write tests for the tests. But then your tests for the tests still kind of rely on your implementation to know what things are tested or not. So you write another implementation, you write tests for that, then you write tests for those tests, and then you reapply those tests to the original tests, and now it's less likely that you skipped something. I'm not sure at what point it makes sense to stop, but I don't know, I keep finding value, but the deeper I go, so I just keep going. And this day we have LLMs, so I can also tell it, cool, okay, I've made an implementation and some tests. Now write a completely new implementation, go. Great, now write tests for your thing, great. Now break your thing and check that your tests catch that, great. Now do that a 1,000 times, find all of the ways you can break your implementation, write tests for them, make those tests reusable, and then apply those tests to my implementation and see if they catch something. And there are things you can do with LLMs. It's fun. I don't necessarily recommend making the LLM write the first implementation, but then using it to test the hell out of it is fantastic. Side channels, you can build everything to work perfectly. All of your libraries are great, specifications are great, and then somebody puts a oscilloscope on your memory path, and they just speed it out, or like they read the electromagnetic fields that your computer produces, and they realize that actually it takes a little less electricity to multiply by 0 than it takes to multiply by anything else. And if you just know where the zeros are in the intermediate computations, you can recover the key. They do that all the time. But those at least require physical access. But then there's the timing side channels, which some think are just a lost cause, and I don't have a formed opinion at this point. But in general, you want your code to take the same time, regardless of what the secret is, because otherwise somebody will measure how long it takes you to respond to something and evince the key from that. Yeah, that's bad. And so you write your code to be constant time, and then the CPU designers over at Intel go like, you know what would be fun? It would be really fun if we just made this instruction take some different time based on what it prefetched beforehand, you know? Yeah, that would be cool. That would be faster. Cool. And then 5 years later, we find out that our stuff is broken because it just reads memory and does things that take different time based on it. Like, anyway, possibly the most frustrating part of my job. Just the CPUs just don't do what we tell them to do. And then they even had the gall to add a flag that you can set in the CPU to say, hey, actually do take constant time for constant time operations. Okay, cool. How do I set that flag? So it's just one of the processor-specific registers. Okay, what does that mean? Well, you can set them. At the end, you look at the giant tool, and you find out that to set them, you need to be ring 0. Ring 0 is the kernel. So you're an application, and you're like, great, So I want the thing to take constant time, and you just told me I cannot set it for everything because otherwise your processor will be slow and you'll be sad and okay. So what do I do? And so far we don't have no answer. So now we have a mode to do things constant time, and they can tell us, oh, but you haven't enabled the mode, so it's your fault. But we don't have a way to turn on and off the mode. I love CPU designers. They're great. Cool. Then recap, and then project preparation, because the exam will probably be a project, because I don't want to do the thing where I sit and like try to gotcha on things. Like we figure out an interesting thing to build, you build it, you explain it to me, exam. Okay, questions about the program? You can't not have questions on the entire program. I just I just dropped. No.
Why did you say about, like, for example, RSA and something else that is not useful now?
Yes. Haha. So, quantum computers. For the past 30 years, we've been told by physicists that in 10 years, at each given time, there will be quantum computers. And quantum computers are not really computers, but they're like ways to create superposed probability distributions of state in such a way that then you can apply gates to them and then collapse those states into an answer in such a way that you would never be able to represent all of those states because the states are exponential in a classical computer. This is probably a bad explanation. I am not a quantum physicist. There is actually a decent explanation in the book. If you have the second edition and you go to the chapter 14, quantum and post-quantum, has a decent explanation of like decent as in understandable explanation of quantum computers. I don't need to know anything about it. Well, sort of no. But point is, you can write algorithms that run on those capabilities. And those algorithms tend to be very good at anything that involves frequencies. Nonlinear symmetric cryptography, mostly not affected. You might hear that there's an algorithm called Grover's, which makes it possible to search as arbitrary space of in a squared time. So if there were 2 to the 128 keys, you could search them in 2 to the 64 time. Wrong, sort of wrong. Sure, you can, but you need infinite circuit depth to do that. As soon as you bound circuit depth to something reasonable, like say a lot more than the biggest classical computer we think we can build, then you start having to parallelize the algorithm, and the square operation is over each parallel operation, which means it doesn't scale. Anyway, point being, quantum computers are not magically halving the security of everything, which is something you might hear. But things that do have structure to them that involves frequencies completely cannot swear, right? Completely gone. So RSA, ECDSA, finite field Diffie-Hellman, everything elliptic curves, Shor's algorithm. It can do discrete logarithms, it can do factorization, it can take a public key and turn it into a private key. Now, do these computers exist? I just told you that for 30 years they've been, 10 years away. Well, they are not 10 years away anymore. As of 2 days ago, there's a paper about how they are doable with like probably 10,000 reconfigurable atomic qubits, which are like there are essentially now two categories of research in quantum computers. One have very fast qubits, one has slow qubits, but probably reconfigurable. The fast ones, you still need about 500,000 physical qubits, and so far they've built, I think, like a few hundreds. But those would be very fast. The slow neutral atoms ones, for example, are reconfigurable. They've built, again, around 100, 200. They've just demonstrated in November capturing with optical tweezers 6,000 atoms, and I think they figured out how to move them. And you see how the numbers are getting close to each other. Like we are all very, 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 very uncomfortable with this. And at this point, we are truly at the transition right now of, okay, well, damn it, this is it. A year ago, this course would have been different. A year ago, we would have, put post-quantum cryptography in like a little chapter because the specifications were super fresh. Deployment was still almost non-existent until a year and a half ago. And now I think we're just going to talk about pre-quantum stuff as legacy stuff you might encounter, but not as stuff that you will use. Because by the time you get your hands on anything practical, nobody will be deploying this stuff anymore. And this is weird. And a lot of cryptographers have not come to terms with this yet, because we have not had a transition like this ever in our careers. The last thing that broke was SHA-1, hash function. It broke in the sense that you can find collisions, which is bad-ish. Like hash functions have a bunch of properties, and a collision is the weakest one. And some protocols require protocols. It's all about protocols. Some protocols require collision resistance, but many don't. So it's fine. And also, it was just a matter of taking SHA-1, tossing it out, taking SHA-256, which was just the next iteration, putting it in, done. And even that took us years. And no, quantum algorithms are both not as complete. Like there are some things that we just don't have post-quantum algorithms for. Non-interactive key exchanges is an example. We could do them with Diffie-Hellman. We just don't have an algorithm to do them with post-quantum algorithms. We thought we did. And then somebody broke it on a laptop. Isogenies. Could have been good. Anyway, and they're also larger, a lot larger. ED25519 signature, 64 bytes. MLDSA signature, which is the post-quantum thing, 1,312 bytes. Yeah, it's gonna be fun. Anyway, I feel like I might have fast forward a couple of terms here. When I say post-quantum, it's just the algorithms that are not broken by Shor's algorithm. They're just the asymmetric stuff that we think does not have an efficient quantum algorithm nor an efficient classical algorithm to break it. And NIST, the National Institute of Science and Technology, it's the American entity that does standards for many things, including peanut butter. You can buy a jar of reference peanut butter from NIST for $1,000. But they also make cryptographic standards, and they run a whole international competition to do in multiple rounds to review different cryptographic post-quantum algorithms. And they've selected a few, and they've also said that they're going to select more in the future, which is now completely useless because there's no more time. It's an interesting time to be a cryptography engineer. The timeline we are getting from people that know stuff, and at this point possibly know stuff that's not public. And they say ominous things like, so here's what I can tell. In 1939, these scientists published an article about plutonium fission. In 1940, they wrote this memo and they did not publish. This is all I can say in public about quantum computers. I'm like, oh shit, okay. Okay, first. Second, and if you do an exercise of risk assessment, this is just bad. I'm not sure I would bet my house on a quantum computer existing in 3 years, but I can't bet my users' lives on the quantum computer not existing. And this positive part of this is the latter. I'm not betting on whether it will exist or not. I am doing the risk assessment of whether or not I can deploy something and stake my users' safety. Because we'll talk about the moral card of cryptography and like what cryptography does to power and so on. But also, dissidents get dismembered when they get caught in some places, and they use cryptography not to get caught, and that's the job. So no, I think the time to deploy anything that's vulnerable to quantum computers is gone. And so we're going to mostly talk about post-quantum stuff. And yeah, it's an interesting time. Lots of people are talking about the post-quantum transition and migration, and there's also a lot of, where there's money, there's scams and so on. But yeah, it's interesting time to be alive. So I did redo most of the program approximately a month ago. Anyway,
yeah,
good time for a break.
Yeah, I think
questions first and then break.
I have questions, but I
Yes.
guess wait after the break.
Well, let's do after break. Okay. So that was a bunch of intro and a bunch of program and so on. Now, this lesson is chapters 1, 2, and 3 of the book, which are similarly just setting the foundation. The first part is, what does cryptography do? Cryptography writ large, of course, it encrypts things, of course, it does digital signatures and so on. A general way to think about it is that it extends trust. It makes tools to extend trust. And it turns, even better definition that I like is that it turns a secret management problem into a key management problem. You have a large secret, for example, and you don't want to, put a guard with a gun in front of the hard drive of that. Instead, you encrypt it, you use cryptography, and now you have the problem of where to store the key, which is a simpler problem because that key can be stored much more easily because it's small. Well, keys were small. And then it allows us to structure power relationships or connections using asymmetric cryptography. But we have the last lesson for that part. Cryptography engineering, we've talked about how it's about implementing things, composing them, actually taking the tools of cryptography from the book, from the specifications, and actually implementing the software that we end up using, making a protocol and then implementing Signal so that you can actually chat, or implementing disk encryption so that if your laptop is stolen, people can't just read your documents, and so on and so forth. It's usually an exercise in threat modeling. So thinking about threat modeling is the activity of figuring out what your attacker is, what can they do, what are their limits. Because again, if your threat model includes physical kidnapping, it's going to be a lot harder. There's this famous XKCD, which is about how in the real world, sometimes it's not the crypto that matters. There are still things you can do sometimes with cryptography. For example, if you add a new laptop linked to a WhatsApp chat, two things that are interesting will happen. You might not notice them, but one is that your phone will ask for Face ID before doing that. Can you think why? It's creating an encrypted connection between your laptop and the phone so that your laptop can see the encrypted messages so that you can chat from your laptop. Great. Why does it need Face ID for that? It doesn't. But in the threat model of domestic abuse, your abuser might know your PIN code, but probably does not have a face configured in Face ID. And at least it will have to point it at your face, and you will know that now your messages are monitored and can act accordingly. The other interesting thing that will happen is that an hour later, you're going to get a notification that says, you connected a laptop. It's kind of weird, right? Yes, an hour ago, I did a thing. Why? Can you think about why?
Because maybe you go to work.
Because now maybe you're at work. And now you're safe enough to see the notification and act accordingly. Anyway, threat modeling is everywhere in the actual engineering of doing things. Don't roll your own crypto would be a whole conversation, and if we have time, we talk about it later. Now, many cryptography courses start with a history of cryptography. I find that extremely boring. Cryptography is nothing like it was before computers. It's not the same field. If you're interested in classical cryptography, there are actually some really interesting things around it. I can recommend Between Silk and Cyanide by Leo Marx, which was about all of how they did cryptography in the Second World War, and it has nothing to do with what we're going to talk about. I mean, some of the threats and the threat models were similar, but that's it, because before computers, it was all essentially just a game and cat and mouse of trying to move things fast, scramble them enough that you can figure them out. Now we do things a lot more structured way. So we're going to skip that part of history. I want to talk a little bit about the difference between the cryptography engineering in the 2000s and cryptography engineering in the 2020s. Aside from quantum computers, but also in general, how we think about a lot of this has changed. We've started, first of all, recognizing that easy to use cryptography matters sometimes more than its theoretical strength. We still want it to be theoretically strong, but if then it's hard to implement securely, might as well not be secure. We've come to realize that if you make something hyper-parameterized that supports all the options, one thing can do everything. You can use it with that key size and that key size and that algorithm, and if you have opinions, you can swap things. People will use it wrong. Or worse, there will be negotiation issues where you can trick computers into thinking you're using one thing when actually using another thing. And one of my favorite ones is JWT, which is a protocol that keeps getting implemented wrong because it supports everything. It supports, it's in theory just a thing to make a signed token, like a thing that says, oh, you're user number 1, 2, 3, and here are your permissions. And here's my signature, so I will know. Great. It supports symmetric signatures, where you have the key and the signature requires the same key to check it, which makes sense. I make the token, I give it to you, you come back to me later, I look at the token, I have the key, I can check that you didn't change it because only I have the key. Cool. It supports asymmetric signatures, where I sign it, but then he can verify that I signed it without my key, which are like, yeah, sometimes you might need that. So cool. Implemented in the same then protocol. And then for some reason, the signed token specification also supports unsigned tokens. Sure. And so you can just say, oh, this is unsigned. And then some correct implementation will go like, no, I want it to be signed. But a convenient implementation will go like, oh, yeah, thanks for the token. If it's signed, I'm going to check the signature. If it's not signed, I guess it's not signed. Good enough. Why does the secure token spec have an unsigned token mode? I don't know. Anyway, this was very popular in the 2000s. Like everything supported every mode and was like you had to make things more parameterized because what if that breaks tomorrow? You have to be able to change it. No, things generally don't break. Like this quantum computer stuff is the first time in 20 years after SHA-1, which also didn't really break. It's the first time that an algorithm actually breaks. Most of the stuff that breaks is in the stuff you build on top. And if you build a bunch of stuff on top to be able to swap things out, you have more things that can break, not fewer. So this is kind of an opinion, but it's getting towards consensus now. 10 years ago, it would not have been consensus at all. So that is a big shift that's happening. In general, making things fully specified from the start to the end. Another difference, the old signature algorithms like ECDSA would tell you, well, a public key is 2 numbers. Numbers, you know how to do numbers, right? Yeah, there are 256 numbers, very large numbers. Moving on. You take them, you multiply them, you do that. And you're like, my computers don't do numbers. My computers do bits. My computers do bytes. I have to send those numbers in a format. Can I have a format? Yeah, sure. You know, there are 2 numbers. You could, for example, put first one and then the other, or you could put the length of the first and then the number and then the length of the second, and then we had 15 different ways of encoding them, and then people would get them wrong, and then there would be vulnerabilities. The new algorithms say, yep, a private key is 64 bytes.
The bytes.
The public key is large. It's 1,000 whatever bytes. That's the public key. The algorithm to take the private key and the message takes these bytes, make these bytes. This is your algorithm. The entire thing is specified top to bottom. That's how we do things now, not how we used to do things. And so much work to then build the rest of that out. Cool. We talked about symmetric and asymmetric cryptographies. I mentioned earlier how symmetric is essentially combinatorics around non-math core. Symmetric encryption is usually just taking a thing that we think has so little math that you can't reason about it using math. Like you take the bits and you rotate them, and then you XOR them, and then you scramble them, and then you take half of them, and you do stuff with them, and you try to make that stuff as non-linear as possible, so that you can't represent it in a way that you can reason about with math. Then we say, okay, that is a thing that we think you can't invert. That is a thing that we think does this thing. There are no proofs around that. Those are just proved by people have tried. And usually you do it by making it do it multiple times. We call them rounds. In symmetric cryptography, things are parameterized by rounds. And rounds are picked by guessing. There's a fantastic paper linked in the notes called Too Much Crypto that makes the argument that we do too many rounds of all this stuff. And then you publish it, and then people break, 5 rounds. And you're like, right, 5 rounds sounds right. My thing has 12 rounds. So if you can break 5 and that's the best you can do, then that's probably good. And that's how we just say those words. And then you make the smallest little component that's based on that. And then you do just combinatorics on top of it, because you just reason, okay, so if I do it 4 billion times, what are the chances that by complete chance these two things end up equal and the attacker can see it? It's just, your probabilities and combinatorial exercises. Symmetric is actual math. Asymmetric is like the hardness of the discrete logarithm problem. It's lattice-based ring learning with noise problems, which I cannot teach. That's the theoretical cryptography that is out of my domain. So I treat them approximately the same way. The mathematicians tell me, if you do that and that, if you multiply two large prime numbers, there's no way to go back to the prime numbers if you just get their product. And I go ahead. Noted. Good. Let's build the rest. So the fundamental tool of symmetric cryptography is generally XOR. Do you already know what XOR is? Yep. Just to have a diagram. XOR is this table here. The reason it's useful is that if I flip a coin, I don't tell you whether it's heads or tail. And heads is 0 and tail is 1. And I tell you that a secret value, like whether tomorrow I will do something or not, XORed by my coin is 1. Did I give you any information? I give you none. Because if you don't know the flip of the coin, if I told you it's 1, if the coin was 0, then it's true. Tomorrow I will do the thing. And if the coin is 1, tomorrow I will not do the thing. And just because you know we're in this box, you know nothing. We use that all the time because you can imagine how to make a rudimentary and information theoretically secure cipher from this. Imagine that you have a secret, which is a lot of bits, just a lot of random bits, and random is important because there needs to be no way to predict it. So you just flip a coin many, many times and you write down 1, 0, 1, 1. And then you make a copy, you put it somewhere else. And then when you want to actually send the message, can you imagine how to use that? You XOR each bit of the secret message of the thing you're trying to send with the thing you had randomly selected in advance. You send it over any channel, and on the other side, you XOR it again. XOR is associative. What's the word? No, it's not associative. If you do XOR twice by the same thing, you go back to the original point. So if you XOR by one and then by one again, you go back to whatever it was before, and by 0, nothing changes, and then by 0 again, nothing has changed. An involution. If you XOR once on the sending side with the same bit stream, and once on the receiving side, you get back the message. And anybody who observed the XOR message learned information theoretically nothing. Does that make sense? So that is the core tool of all of symmetric cryptography. Usually, courses, books start from that and then go straight into how to, but the problem with that is that the key is small. No, that is not the problem. Sorry, that the key is large. I mean, yes, that is a problem of the one-time pad, but that is not the problem. Can you think of another thing you can do if you're the courier? Let's sketch out the entire thing. You have a large book of ones and zeros, and you make 2 copies of it, and you keep one in one office and one in another office. And when you want to send something, you XOR it by all of those bits and send it over by courier XOR. You cross out every bit you've used, because if you use the same bit twice, now you can XOR the 2 messages together and recover some information. This only holds if you use each random bit once. But you do that, and you send it over. And can you imagine one thing the courier can do? They cannot learn anything by reading it. We just said that there's a completely information theoretical argument that they cannot. They can change it, though. And does it take anything to change it? If you know that, for example, every day I send over a message which says whether to buy or sell a certain stock, and you observe that on almost every day I say to buy, and then once a month I decide that the stock is going down and I change to sell, and they use the one-time pad to send it between the two offices so that the courier doesn't learn if I'm buying or selling tomorrow. What can the courier do to make money? Most of the days I buy, right? So if they XOR the bits of buy with the bits of buy and then the bits of sell, what does the message say now when you decrypt it on the other side? It says sell. Because if you XOR it, you can XOR things in and they cancel out, right? So if you know that the first 3 letters are buy, you can XOR the first 3 letters with buy, and now they're all zeros. Then you can XOR again with sell. It's 4 letters, whatever. You XORed also the space. And now those letters say sell when you decrypt it. I don't know the key. I have no idea what was before, but I took a guess that it was buy, and I turned it into sell. Now tomorrow you'll sell, I will buy. You were meant to sell, I make money. Broken. It was informational theoretically secure. It was the perfect, and this is called the one-time pad. And people describe it as the perfect cipher. It ain't. It's actually a good example of how it's absolutely not a complete tool, without even getting to the fact that the key is a whole book, the length of the entire message, which is not very useful. You can do other things. You can... you want to know if a message says buy or sell. You're the courier. You just keep the messages. And then at some point, you want to know if the third one was buy or sell. You give it to the office, and you check if they buy or sell. That's called an oracle. And in general, there are a lot of things shaped like this that happen if you don't do authentication of the message. And authentication is instead the protection of the integrity of the, making sure that the message is the one you sent. Because otherwise, again, you send two messages. One is, this is a little contrived, but I assure you that you can use real world things in the same way. The first message is, announce this on the public blog, and then a message. And the other message is, here is the confidential mail, and then the mail. Ka-chink, ka-chink. You take the first half of the second message, you put it in place of the first half of the first message, you XOR them to swap them because you know what they are. So you can just, you don't know the second part, but you know the first part. So you just XOR out what you know is there, you XOR in the second part, and you send them over. And then you check the blog. And the blog has the secret memo, the confidential memo. You've learned the confidential memo. So you need authentication because authentication instead is how you make sure that the message has not been modified. So it's not either swapped with bits from sell to buy. It's not stitching of different messages. It's not truncated. That's also a problem sometimes. And we formalize these with two things we call security goals. The security goal for confidentiality is indistinguishability. So one way to formalize whether or not something is like, how do you express the concept of something remains secret? The strongest way to do that is to say that if I show you an encrypted message and I show you a completely random message, just random bits, coin flips at every bit, if you can't tell the difference, if I set up a game and I show you the two messages and you have to pick which one you think is the encrypted message, if you have 50-50 chance, the messages are indistinguishable from random, and then we can theoretically show that you learn no information. Because if you can't even tell whether it's random or an encrypted message, by definition, you've not learned anything. If there was any information you could glean from the message, you would glean that information and then be like, well, this one tells me you're selling, this one tells me random stuff, so this one is the message, and you would win at the game. We call these games, simply, and usually combine a security goal, which is indistinguishability for the game of can you tell them apart, or non-malleability for the game of where instead I give you messages, or we'll see exactly how I start the game, and I ask whether you can create a message that is not the one I created, which is instead how you formalize the other notion, the notion that you can't just, change parts of the message. The one pipette is clearly not non-malleable because you can swap bits. The games, you set them up with in models. The one I described is, well, we talked about a few of them, but the ciphertext only attacks are the ones that you might think about most instinctively. It's a game in which I only show you the ciphertext. I show you a bunch of ciphertexts, and then I ask, okay, tell me which ones are messages, which ones are random. And if you can tell them apart with better than 50%, that's your attacker advantage. And we want that to be very small. We'll see how we measure it. But in general, we want you to have essentially 50-50 chance of doing that. For the non-malleability, instead is you just see a bunch of ciphertext, and I ask you, okay, here are 100 messages, 50 are random, 50 are, no, not even. Here are 100 messages that I made, and they're encrypted. Give me back another message that I didn't make. If you can do that, then you broke you succeeded at the game, you broke non-malleability. But you can set up much more powerful attackers to simulate the fact that they can usually do something else than just looking at the thing. So one is known plaintext attacks. In a known plaintext attack, you also let the attacker send you a plaintext, and you will give it back encrypted. So in the known plaintext attack, for example, you send me however many messages you like, and I give you back the encryption for each of them. Then I encrypt a message that I don't tell you, and I give you the message and a random string. If you can tell them apart, broken. Now, this is a little more useful because it lets you learn things about the ciphers and learn things potentially, if the cipher is bad, about the key. Imagine something where you can figure out the key by looking at the encrypted message. You would ask, hey, can you send me back ciao encrypted? You would use it to recover the key, and then you would use the key to decrypt the message and you win the game. If you can't win this game, it means you can't extract the key from the ciphertext. We've already gotten a nice real-world property out of this this game. We can make them stronger. Known plaintext. I was mixing them. Known plaintext, it's not you send me ciao and I send it back encrypted. Is I tell you, here's an encryption of ciao, here's an encryption of foo, here's an encryption of bar, here's an encryption of something I'm not telling you, and here's a random message. Which one is the random message? We can do a stronger one where you get to choose the plaintext so that you can see how that makes the cipher work. And in general, in cryptography, modern cryptography, there's what's called Kerckhoff, I hope it's pronounced, Kerckhoff principle, which says that a system has to be secure even if everything is known about it except the key. In general, there isn't anymore the secrecy around, oh, we can't reveal what our super secret algorithms do because that will give a leg up to the adversary, and like, or, oh no, they capture a U-boat and so they have captured the Enigma machine and now it'll be easier for them to figure out how to attack it. We do none of that anymore. The code is open source, the algorithms are specified. The only thing that holds the security of it is the key. You know the key, you can do the thing, decrypt, sign. You don't know the key, you can't, even if you know how everything else works. And the chosen plaintext attacks let you exercise that. Like, even if I can cause some messages to be encrypted, I don't know the key, I know everything else, I can't use that to figure out how to decrypt the next message. Finally, there's the strongest one, which is the one we actually use. We actually try to use. We try to make available so that you can build things on top of, is a chosen ciphertext attack. In a chosen ciphertext attack, the oracle can do two things. It will both encrypt things that you send it, but it will also decrypt any ciphertext you ask. And you might be asking, okay, what the hell is the point? The game is then decrypting a message that was not sent to the oracle. And sometimes you can actually do this. There are settings in which you can cause the system to do things which are not, however, encrypting that one message that you're trying to then decrypt. And then you observe that one message you don't know. Because, for example, there are many users and they encrypt messages with the same key. So you can ask, hey, can you encrypt my backup? And then you can also ask for your backup to be decrypted, but will refuse to decrypt a different backup. There are different settings in which this can make sense, but it is the strongest setting you can construct, because now the attacker can do anything except decrypt that one message that you are hiding from them. So when we say that a cipher is in the CCA, it means that it's indistinguishable from random in a chosen ciphertext attack setting. And that's the gold standard for key exchange algorithms. You can easily port this concept to asymmetric cryptography where there's public and a private key. In general, we use these games to reason about the components so that then we can compose them. We can say, as long as the key exchange is in CCA, then this protocol we build around it will work. And you can do reductions of security by saying, if you could break this protocol, you could use it to mount a distinguishing attack on the key exchange. So if you can turn it around and say, let's pretend that you can break this protocol. Okay. Now, by breaking this protocol, you can turn it into an attack of the key exchange. That means that if you use a key exchange that's not broken, the protocol is not broken because per assurdo, by contradiction, you've proven that the security of the broader system reduces to the security of the component. Okay. Time. Yes. Questions about this? Yes. These games are kind of fun to also just play with it and try to figure out, like, for example, taking the one-time pad we discussed and trying to instantiate it in each game and see which one fails and which one doesn't. It's sometimes a little counterintuitive. Also, next week we'll talk about ciphers and hashes, and we'll use these notions a few times to say, well, if you compose them like this, it looks like it's fine, but then, and it's not. But if you can do a chosen ciphertext attack, you can do that and that. I just want to have these notions to reuse. Okay. Let's look at computational security first, since we've already talked about Kirchhoff. So when we say secure, the one-time pad is secure because it just has a key the size of the entire message. Keys are not that large. That would not make sense. So usually instead we have a smaller key. For example, a key that is, for example, 128 bits. We need to be able to quantify the security of a system. And one way to quantify it is to say that the attacker has a certain advantage in the game. What advantage does an attacker have if the key is 128 bits against in the CCA game? Well, they can always try all of the 128 2 to 128 bit keys, see which one decrypts the message, and once they find it, be like, that's the message. So they have a little advantage compared to the perfectly informational theoretical setting. We quantify that as that advantage, so that's going to be 2 to the minus 128, which is how little chance they had. We quantify that in terms of how much work they need to do to gain that advantage. And you usually express that as a tuple. So if they do this much work, they will have this much advantage. If they do 2 to 128 work, they're going to have an advantage of 1 because they will find the key and they will win the game because they will point to the message that's encrypted because they found the key by trying them all. Can you count to 2 to 128? No. And this is surprisingly controversial. Like a lot of CPU and a lot of human cycles are spent discussing if we need higher security levels, and we don't. There have been 2 to the 88 nanoseconds since the start of the universe. You can do a lot of these fun arguments, like if your operation is moving a single electron by a single energy level, you would need the energy of the sun to do 2 to 128 operations that are that cheap. There is no counting 2 to the 128. Security levels are a remnant of classical cryptography, when there was an actual trade-off between security and how long it took to do the thing in the field. And so you had to decide whether something was, secret, confidential, secret, or top secret, and use the right cryptography based on that. And so we got the 128, the 196, and the 256 security levels. Secure, secure, and secure. Like there is only one security level, which is secure. And sometimes 128 bits are not enough for secure, because if you're worried that you're a large company, you encrypted 2 to the 64 messages, how much work does the attacker have to do to decrypt one of them? With an advantage, with a probability of let's say 2 to the minus 1. So 50-50. Not a lot. They can do 2 to the 64, try 2 to the 64 keys, and they will probably hit one of the 2 to the 64 keys that you had. Each message is encrypted with a different key in this setting. So you have 2 to the 64 users because you're a large company that has a lot of users. And then the attacker just wants to break one of them. Will be happy if they can steal one person's money. They will try 2 to the 64 keys, and statistically, they will probably hit at least one where there's a collision. So you don't have what we call 128 bits of security, because now the attacker can do 2 to the 64 work and reach a goal. And here the goal is the multi-target setting. The multi-target setting is the setting in which you have multiple targets that are acceptable, and you don't want to break them all, which instead would be 2 to 128 work, but just wants to break one of them.
But you still need to like do some computation for each.
Yes. You do need to do some computation, but not for each of them. You can make that log n. You can build a lookup tree of their, for example, you know that all of the encrypted messages start with a header. So you build a tree of all of the ciphertext. You go through all of the keys. For each key, you encrypt that header. You do a search in the tree, which is log n. If you get a hit, done. So yes, it's not y to the 64 to the 64. It's going to be 64 2 to the 64 times log base 2 of 2 to the 64, so 64 2 to the 64 plus 64 work to times 64 work. So it's 64 plus log n of 64, log 2 of 64 work to get an advantage of 2 to the minus 64, which is unacceptable. So there are settings in which we do want more than 128 bits of space of key, for example, but not because we need a security level higher than that, but because in some settings, the security level does not match the key size. In some settings that you have to think about, for example, multi-targets and so on. So you express these as the tuple of, given this much work, what's the advantage of the attacker? So what is the advantage is just the chances of success of the attacker. In this case, 64. I should know this, but 6. Okay, so in this case, you have 2 to the 70 work gives the attacker 2 to the minus 64 advantage. Bad. Okay. You usually pick a target for the advantage. A standard is usually 2 to the minus 32. You want the attacker to not have more than 1 in 4 billion chance of success. And then you fix that side, and then you say, okay, so how many bits of security do we have is the amount of work that the attacker will have to do to reach 2 to the minus 32 success chance. And generally, you try to keep the work above 2 to the 128 and the chance of success at 2 to the minus 32. That's generally the benchmark. It's not like they are obviously made up numbers. Like it's not like 100 to the 120 is doable, nor is 2 to the 100 probably. All of the Bitcoin network has done in all of its history something like 2 to the 90 operations, something like that. You would need 1,000 times the Bitcoin network run for the entire time the Bitcoin network run, assuming that each operation is as cheap as a single hash that the Bitcoin network does, which is not going to be the case, just to get to the 100. But we just find 128 like comfortable and reassuring and round and 2 to the minus 32. It's what people seem to use. NIST uses that. Again, once you make that one big enough, it doesn't really matter what chance of success it gets the attacker. Sometimes they don't move linearly one to each other, but Okay, so that was secure exponential. Generally, we talk about an algorithm being secure when the algorithms to attack it are exponential. Brute force is exponential. If there are 128 bits of key, how many operations do you need to do to find it? 2 to the 128. Going on. But in general, as long as the key size is in the exponent, we are happy. Things like RSA, things like also the lattice stuff have more efficient algorithms, which are significantly more efficient, which is why, for example, for RSA pre-quantum, you would use keys of 2000 bits because there are more efficient factorization algorithms, but they're still exponential. And as long as things are exponential, it's fine. You can just make it a little bigger, and the attack cost goes. The important thing is that growing the key outpaces the attack fast enough that you can just grow a key a little bit if they make the attackers a lot better. Like if the attackers got a lot better, you make the key longer by a few bits, and you're ahead enough. Anytime there's an attack that's polynomial instead, where the amount of work is not in the exponential, we kind of consider that broken, because you could try to still play the cat and mouse game of how much work you do versus how much work the attacker does, but it doesn't give you that completely outsized advantage that the exponentials give you. Other things to consider is that sometimes it's tolerable to have less than 128 bits of security when the attacker is sequential. All of these attacks we've talked about, attacks that you can scale usually embarrassingly parallelly, meaning that brute force scales completely parallelly. You have 2 to the 64 keys to search. Do you have 1,000 machines? Great. It now takes 2 to the 54 time. Do you have 1,000,000 machines? Great. It now takes 2 to the 44 machines, because you can just split up the search space, assign it to the different machines, run them in parallel, and do a lot of work. If something requires doing things sequentially, which some attacks do, like some attacks require an oracle where you have to send a request to the target and the target has to answer, and then you have to change a little bit based on the response what you send back. Anything that serializes like that, 2 to the 50 is probably fine. 2 to the 64 is probably fine, because there's no way to do 2 to the 64 sequential operations, because let me bring back up solver. I'm so going to show something I should. Anyway, I have a little tool I like to use to just do these kind of operations, but 2 to the 64 nanoseconds to years. I think it's useful to get an intuition for these sizes because even if you can make each step of that operation take a nanosecond, which probably doesn't, nope. And it's useful to get intuitions for these things because computers are very, very fast. So sometimes you're like, oh, that's impractical. We can't store that for every user or something. Then you do the math and, oh, that's a gigabyte. Okay. And other times you can figure out the actual running time of an attack is not a concern. We've talked about multi-target attacks. We've talked about reductions. This paper here is the too much crypto one I was telling you about, the one that makes a very convincing case that some of the arbitrary, no security proof stuff we do with rounds could have fewer rounds because people have not been breaking anything in the last 20 years after SHA-1, which we kind of knew was broken. Like almost from the start, people start finding breaks in SHA-1 very early. So even that, I'm not sure how much to count that. Formal proofs. You had a question about formal proofs.
Yes. So the question is, how much of this is formally proved to be correct, and how much this actually plays a role in the field?
So formalization of proofs shows up in 3 places. One is the actual asymmetric theories. There's usually some problem which is theorized to be difficult, like discrete logarithm. And then the actual math that shows, assuming the hardness of the discrete logarithm problem, then you can do that, you can do that, you can do that. And that usually has formal proofs that get you to the bottom of that. Second, there's formal proofs for protocols, things that show those reductions I was talking about. You can use lean, you can use symbolic execution, you can use a number of formal techniques to show that assuming that this box is in CCA, assuming that this box is, then we can reduce the hardness of this protocol to the hardness of that. That has a lot of success. For example, things like the TLS 1.3 protocol was proven with formal methods, and that was probably useful compared to previous iterations of the protocol, where sometimes we realized afterwards, oh yeah, you could do that. Damn it. Like SSL v3 is notoriously broken. Some of the symmetric cryptography, you can just do the proof by doing the combinatorics, and like, I don't know how much people think of those as formal proofs, but you can write the security statement. And finally, there's the entire field of formally verified software, which is taking the software, building a model of how the software is executed, and trying to prove that the software corresponds to a specific abstract specification. I think it's a useful tool. I think its return of investment is not as high as making test vectors. But this is a kind of spicy opinion. But yeah. Yeah. So there are some boxes that are just very not proven, and proofs connecting some of these boxes, and then the software on top of it, which maybe matches the specification. Okay, last thing I want to talk about was randomness. It's if I go over by 5 minutes, do you need to run? Okay. Okay, then randomness. Okay. We mentioned randomness a number of times. The random coin flips, keys need to be random, because if they're not random, you just predict them and you know what the key is, and the entire thing comes crashing down. The formal concept of randomness is entropy, which I think is for distribution of probabilities, each probability multiplied by the logarithm of the probability. And when something is completely random, you take its entropy, and it's, for example, for a random 128-bit key, there are 2 to the 128 possible states. Each of them has 1 over 2 to the 128 probability of appearing, because it's completely uniformly random. And you add up those, and you get 128 of 2 to 128. Is the entropy the exponent or the? It's 128. You get 128. That's the entropy of that key. Why? Because if some states were more represented than others, you would learn less information by knowing which state it is. And the maximum entropy you can have in a 128-bit string is 2 to 128, because that is the completely uniform state. So generally, we do want to be able to get random things. We have a tool which we're going to look at how it works in future lessons, which is the cryptographically secure deterministic random number generator. It's something that takes entropy, so some unpredictability, which, however, can have any distribution, and produces a stream of perfectly uniformly random bits, where the only way to know they're not uniformly random is to know everything that was in the input, so that you can then just reproduce it. It's a completely deterministic algorithm. If you give it the same input, it gives you the same output. But if you change even a single bit of the input, everything changes completely, and there's no way to correlate those. So you can play those indistinguishability games with their output. These tools work. These are completely solved problem of cryptography. And for the longest time, this was not a consensus opinion amongst some operating systems. So for example, usually how that entropy is collected on your computer is the job of the operating system. The operating system observes some things that are hard to predict. The timing of certain instructions, interrupts received by the keyboard, by the hardware, a lot of stuff. It puts them into that pool of events such that unless an attacker can predict all of them or brute force all of them, they will not know the state of that pool. And then exposes to you CSPRNG to get randomness out. And for the longest time, Linux had this mechanism where it would say, well, if you've read 128 bits, you've reduced the entropy by 128 bits because you might have used those 128 bits to learn 128 bits of information from the input pool. And like, no, cryptography works. There is no way to go back to the input. This was very painful for a long time because it would block and say, hold, I have to collect more entropy if you want more entropy. Because what? Once you have enough entropy, enough unpredictability in the system, there is just no way for the attacker to know what the input to the CSPRNG is. You can give it however much output you want. It will never know what was the start, if the start is large enough that it can't be brute forced. Is the start large enough not to be brute forced? Depends. A lot of small devices don't have a lot of entropy, and especially if you try to create a key as soon as they boot, because maybe they want to do something immediately. Maybe they have done nothing yet. Fantastic research on this is the factorable.net link, which was a scan of the internet, which found a lot of devices that had the same key by chance because their pools were just pretty much uninitialized, like always the same stuff at every boot. And since they were just made the exact same way, the same chip, the same software, they didn't have enough entropy in the system yet. The OpenSSL link here is another wonderful bug that has to do with randomness, where instead somebody patched the software and by mistake removed all of the sources of entropy except just the number of the process, which is 1 to 65,000, so a very small space that could be searched. And then that was used for a while as the thing to generate keys, and that was bad. These are all things that happened many years ago. This is mostly a solved problem. These days, your CPU has an open physical loop that just essentially measures thermal noise. Your operating system will use that plus a few other timings of events, put them all into a pool, and then you can ask the operating system, hey, 32 random bytes, and it will give you 30 random bytes. The only way this breaks today is when people try to be smart. Is when people try to be like, well, but what if the operating system is backdoor? Why are you running on a backdoor system? Why do you think you can win a game where you're running on a backdoor system? Yeah, but what if I'm going to add things and sample them and like take random keys? And you know what happens? They introduce bugs. And those bugs actually make things less secure. So solve problem, the operating system has a CSPRNG. It's called get random on Linux. It's called sys something unpronounceable on Windows. It's called get entropy on OpenBSD. You probably don't even have to think about it because your programming language probably has a single API call that you call and say, random bytes, please. And it goes to the right thing in the backend and brings them out. That's my job. In Go, it's called crypto/rand.read. And for a while, it returned bytes and an error if something failed. It doesn't return an error anymore because a computer operating system that doesn't have random bytes is broken. So we just exit the program. If we could, we would set fire to the CPU. It never happens. The APIs never fail because that is a solved problem. I think that's it. Questions about this? This part is foundational because then we'll talk about generating keys, generating random nonces, generating random this, random that. That's the sole problem that we can leave over there. There are settings in which you might not have this, like smart cards where you're worried about the attacker being able to extract everything that you're computing, there you have a problem. It gets very hard to do cryptography without a good source of random numbers. But by and large, all of the things we deploy cryptography on these days have good sources of random bytes and an operating system that can shrink wrap them, run a CSPRNG on top of them, and expose you an interface. Questions?
Is there like you said because about this entropy random numbers, so like small devices that might be might have the same code by chance, but there's like, is there a threshold after like I don't know how much time that we have
they diverge sufficiently? So that is the exercise of measuring entropy input, and it's hard. Like, it's actually very hard to tell how much entropy each event has. Like, you press a key. How much entropy does that have? You've observed how long that took. How much entropy does that have? It depends also on the resolution of your timer. If your timer has nanosecond resolution, you get more entropy in the information of how long that interrupt takes than if it has millisecond resolution. Because in millisecond resolution, it might always take one. Congratulations, you gain nothing. So since it's hard, we try not to play that game. We try to instead say, look, you're a CPU from the last 15 years, right? I can just ask you to run your little open physical circuit that just returns random stuff based on the temperature, on like background temperature noise. Like, let's just run it 1,000 times. Put it into the entropy pool before we boot and move on. Because we have the exponentials on our side. So we can do a thing 1,000 times, and now it's probably 2 to the probably hundreds of different possible states. It has hundreds of bits of entropy, sufficient. Because again, there is one security level. And by the time we have 196 bits of entropy, because it is a multi-target attack. Like, you can imagine if we only had 128, and then we generated a key, that would be the thing we described before, where you can get all of the keys and try to attack even a single one. So entropy is one of those things where you do want more than 128 bits, because you probably are playing a multi-target game. But yes, we just collect a bunch. Well, like, prove that it's like, show that usually the distribution is such that there's at least 0.1 bits of entropy in each, and then we run it 2,000 times and move on. Yeah, it's a hard game. The best choice is not to play. The Linux kernel used to play the game because it wanted to then pretend those get depleted, and so it would try to. Terrible times. Jason Donenfeld drove us out of that, fixed all of the Linux kernel. Thanks, Jason. But it's a good question. For a long time, people tried to figure out that at what point do we have enough entropy? Like, just overshoot and then move on with your life.